Okay. Right. So today's lecture is going to be very math based. Okay, I'll tell you this straight first. Very math based. We are going to use integration method to determine the shear force and bending moment equation. Okay, and this integration method is very unique. Okay, I would say it's one of the most powerful technique to determine the shear force and bending moment equations. Then after that, we're going to use the elastic curve method to determine slope and deflection of the structure and also solve statically indeterminate loading. So these two topics are related. Okay, these two topics that you see, integration method and the elastic curve method, they are related. If you don't, I mean, the elastic curve method also does integration. Okay, so if you don't know how to integrate, you're gonna have issue. Okay, so that's why we make sure that you have done your math course first before coming up. But the integration technique that I'm going to use down here is very easy. Okay, very easy. Oops, sorry, very easy sort of integration method. Okay, very basics of integration method that is not that complicated like what you learn in your math course. Okay, your math course, we are trying to teach you a lot of different technique. For this case, we are going to just use one technique of integration. Right. So we're going to deal with integration method. Okay. Now, this week I did not post any example because all the example can be hand drawn easily. Okay. So we're going to deal with the integration method. Now, an integration method is only or is very powerful and unique if you have a structure that that is simply supported like this, or can be any structure. Okay, it is simply supported, can be overhanging or whatsoever. And now the structure distribution is unique in the sense that it's neither a gradient or is it uniformly distributed, but it is this sort of format now. Okay, so this is how your load is distributed now. Okay, very unique sort of distribution. Now the advantage of this, okay, so can someone tell me, right? If you have a distribution, so this distribution will have omega as a function of x. Okay, so can someone tell me, if you don't use the integration method, which I'm going to teach you, what is the problem you're going to solve or you're going to find when using the method that I've just taught you, or any other methods that you guys know? Okay, what's going to be the biggest problem? Anyone?
You can divide it by small pieces.
Yep, you can that's a solution procedure. You can develop by you can solve this by dividing to small pieces. You're absolutely right. But why is this difficult? Why do you have to divide this into small pieces? Anyone? Why? Why? Okay.
You want to know the area.
Yep. So finding the area, you're almost right. Okay. So I'll tell you is the area, but what is the most interesting part is this. Okay, it's difficult to find the position of the equivalent load. And the term I'm going to highlight over here is the position. Okay, the position of the equivalent load. Do you agree or disagree first, or no comment? Anyone? Anyone? Do you agree? So let me explain what is this position of the equivalent load. And you guys know about nobody. So if we have the first one, I'm going to sketch out a beam. Okay, so this is our beam. Okay, so the first one that we are going to deal with is evenly distributed. Okay, it's going to be evenly distributed load. So as usual, simply supported structure. Then we have an evenly distributed load, right? And the evenly distributed load is over a distance L. Okay, it's over. And this one has a function that is omega. It's constant, yes or no? Right? So omega as a function of x, this is just equal to omega, right? So now, for this case, it's pretty straightforward, right? So now I'm going to draw. I'm going to move my screen slightly. Okay. So now I'm going to draw the free body diagram. Right? We have simply supported. Oh no, free body diagram. Come on, Eugene, wake up, wake up. So I still call this my point A, my point B. So this is my AY. This is my BY. Then if I draw this, I know over here, this is my equivalent load. And the equivalent load is equal to omega multiplied by L. And the distance, right? And the distance from here to here, can someone tell me what's the distance? Anyone? It is what?
L2.
Yep, L over 2. Absolutely right, right? That is straightforward, okay? So what do I mean by the position is this. Another one, if we have a gradient, okay, another one, sorry. So this one is evenly distributed load. And then if we have another one, which is known as the gradient distributed load, it's also pretty straightforward, yes or no? So if you have a gradient distributed load, it's also pretty straightforward. So if this is your structure now, and then you have a load loading this way, and the maximum value is omega naught, right? So if you have, and then it's spread over a distance over from here to here, this is L, and this is A, and this is our point B. And then now we start to sketch our free body diagram. We sketch our free body diagram. So over here, this is our AY. Down here, this is our BY. Our equivalent load is straightforward, right? Equivalent load is never a problem for us. It's equal to half multiplied by omega naught multiplied by L. Okay, that's our equivalent load. And then we know the distance from here to here, right? We know we are aware of this distance. Okay, so the distance from here to here is 2L over 3. The distance from here to here, right, is L over 3. Right? Those are real straightforward, and I think I showed you guys why that is L over 3 quite a while ago now. Okay, so this is L over 3. Okay, and then over here, hey Eugene, sorry, I'm colorblind. So we know that this is L over 3, and the equivalent load is equal to half omega naught multiplied by L. Okay, now question for you. with the diagram that I've drawn on the left-hand side, right? You guys have seen the diagram drawn on the left-hand side. Getting the area, is it difficult? Anyone? Getting the area under the curve, is that difficult because you are given a function? Anyone? It's not. It's not, right? Because you just integrate between A to B, yes or no? Because you're given a function. But what is the problem? So you can find the equivalent load. You can find the equivalent load, which is the area under the stress strain curve. Okay, under the the distribution curve, omega as a function of x. The problem comes is what? Where is this equivalent load going to be acting on? Right? That is where the trouble is. Right? So for this case, where okay, so for this case, I'm going to do the exact same thing. I'm going to do the exact same thing. So you found a function already. So we know a function, right? So now to solve this problem, we want to find what is our AY, right? We also want to identify where is our BY. Then we found our equivalent load. Okay, so the equivalent load is equal to, you integrate, right, from between A to B, right, between A to B, omega as a function of x dx. This is straightforward, right? This is easy. Now the problem is this. Okay, now the problem is this. Where? What is this distance? Can anyone tell me? What is this distance? Anyone? No answer? Yeah, I'm glad no answer.
Isn't that be where your maximum?
No, it's not. Okay, you can say it's when no, it's not. So you cannot guess. Okay, the load are very precise, the equivalent load. So you cannot find your AY and BY. When this happened, okay, when this happened, you have no other choice but to use what? Integration method. You have absolutely no choice. Okay, or I mean, some of you might say, Eugene, I might maybe I can like I'm not saying I recommend we do this. Maybe we can put loads like this and then put another load like this and then put another load like this, you know, keep on changing the load, right? You're going to put some sort of evenly distributed load and try to, so by the time you finish doing that, it takes way too long. Okay, you can say, oh, I can use the software. Yeah, you can use the software. Why not use something simple, okay, rather than rely on software? Okay, like why not we do something really simple that you already know and already learned already. Okay, so this is where we have to use the integration method. Okay, as I say, it's one of the most powerful technique. Okay, so if let's say you don't have your structure analysis handbook with you, you don't know what's the equivalent load or whatsoever, you just integrate. Okay, this is what I call a real unique method because it's one technique can solve for all. Okay, that's what I like about this method. Okay, so let's look at over here. So I'm going to write to you a relationship where we have dv. I'm not going to prove this to you, okay? By dx, okay, is equal to minus omega as a function of x. Okay, so this is the first formula. Okay, this is the first formula where omega as a function of x, this is the equation of the distributed load. Okay. So now let's say now your distributed load is omega x is on this diagram. Okay, so let's say now we are looking at this diagram now. Okay, where I highlight in yellow. Okay, so we have to find omega as a function of x. Omega as a function of x is not difficult to find. It's real straightforward. You can go to Excel, go into point load. Okay, I'll show you, those of you who are interested later on when I finish class. Okay, if you're interested, I can show you. Okay, it's all you need to do is know x location and loads at different position. Then you plot it out, and then you use the data fitting curve trend on Excel, and you find your trend. It's that simple. Okay. Then from here, you're going to have a first relationship